Hello everyone and welcome to Calculus. Today we'll be finding the volume of a region using disks. Problem number 1. Sketch the region bounded by the x-axis, the y-axis, the line x is equal to 4, and the line y is equal to 3. What is the volume of the solid formed when that region is revolved around the x-axis? So I need to make a sketch. Got a lot of things going on here. I have the line x is equal to 4. I have the line y is equal to 3. And I'm also being bound by the x and y axis. So the region that I'm looking for is this region right here, but not area. We're going to be doing volume today. So how is it a volume? It'll become a volume once we wrap it around the x-axis. So try and picture that. What would happen if you did this? If you want to visualize it, this is what I would have done in class. I would take a pencil. Oops, still on that. I would take a pencil and then I would put a Post-it note attached to it along the bottom and then just spin it around. What happens if you spin this around? So it would go to the same height below and it would go like that. It would make a cylinder. So the hardest part of this section for people is definitely picturing it. And in class, I have all kinds of models and things that I use to help you visualize it. So you're going to have to work a little bit harder at it now on your own, but I know you can do it. So this is pretty easy. We know that the volume of a cylinder is pi r squared h, which in this case, my radius is 3. And my height of my cylinder, you're having to look at it sideways, the cylinder is on its side, would be 4. So I know my answer is 36 pi. But as usual, I'm going to use a very easy example to show you something that we will be doing, that the skill we need to know for when these problems get more challenging than just a cylinder for which we have a formula. So I want you to think about taking this cylinder and running it through a slicer at the grocery store. So you're in the deli department, you take this, what does it look like? Like maybe a salami, right? So you take this salami and you start running it through the slicer. And what starts to fall off of the slicer? Discs, right? As it goes through the slicer, it keeps making these discs. And if you were neat enough, you could pile up these discs nice and neat and actually reform your salami, but now it's all nice and sliced, right? So we're going to use that concept to find the volume. I'm going to add up, which is integrate, all of these discs. What is the area of a disc? Pi r squared. So I'm going to integrate or add up all of these discs. Where are these discs? So these discs are all the way along the length of this. So from 0, I can make a disc, and I can keep making discs until I get to 4. And then what's the radius? The radius is 3. So I'm going to replace this with 3 squared. So now I have the integral of 9 pi from 0 to 4. I'm going to put a little dx here, which is funny because there is no x in the problem, but there will be now that I integrate. 9 pi x from 0 to 4, which is equal to 36 pi minus 0 pi, which is 36 pi. You might be thinking, why would I do all that? There's a formula. Because we're about to do funny shapes that don't have formulas. If I asked you to take this shape and wrap it around the x-axis, you'd be making some goldfish there. But if you did this around the x-axis, you could still have a bunch of discs, and you could still add them up. And that's what we're going to do today. We are going to do one more easy one just to get us started. So now the volume of the solid, what is the volume of the solid formed by revolving around the x-axis, the region formed by both axes again, and the line y is equal to negative x plus 4. So again, I'm going to draw, always have to make a sketch. 1, 2, 3, 4. 1, 2, 3, 4. This is going to be my line. And therefore, this is going to be my region. And I want to take this region and I want to revolve it around the x-axis. So again, you could take your Post-it note that you've put onto your pencil, and here's the sticky side, and you could just trim it so that it's a triangle, and then spin it around. What do you see? Hopefully, you see, if you looked sideways, a cone. And that cone is just a bunch of circles added together. So again, if you took this cone and you ran it through the deli slicer, what would pop off? Circles. It would start with little circles, and then they would get bigger and bigger circles until you had this circle. And if you were very careful, you could take all these circles and stack them on top of each other and recreate your cone. It would be sliced now, but it would be the exact same volume. So that's what we're going to do. The volume is going to be the integral. And where am I going to take my slicer? I'm going to start my slicer maybe here at 4 and go to 0. But for our purposes, we're going to start at 0 and run it through 4. So I'm going to start at 0. I'm going to keep slicing until I get to x is equal to 4. But now the radius keeps changing. So you always want to start with this concept, R. You always want to add up a bunch of circles. You're adding up circles. And so here's the area of the circle. And if you add up all those areas, you're going to get volume. So the area of the circle is pi r squared. So my recommendation is always write pi parentheses squared. So what is this radius? Well, at 0, the radius is 4. And I know that at 1, the circle that happens right here at 1, the radius is 3. And then here at 2, for this circle, the radius is 2. I'm using this formula right here. When x is 2, when I'm way out here at 2, the radius is 2. When x is 3, the radius is going to come out to be 1. And then at x is 4, if I put a 4 in there, I'll get 0, which makes sense. The radius right there is 0. There's no more radius. So what is the radius? The radius is always negative x plus 4. And that radius is going to keep changing from 0 to 4. So now I can do this integral. I can take the pi out, and you could use u substitution, but I'm probably just going to expand it to be x squared minus 8x plus 16. And I'm going to put a little dx there. From 0 to 4, my integral is going to be x cubed over 3 minus 4x squared plus 16x from 0 to 4, which is going to leave me with 64 thirds minus 64 plus 64 minus pi times 0 minus 0 plus 0. I do want you to be really careful. It's so many times when you plug in 0, you get 0, but the few times that you don't, you have to always at least check to make sure when you plug in 0, you do get 0. So these cancel, and I get 64 pi thirds. So I can check that because I know that the volume of a cone is 1/3 area of the base times the height. So the area of the base is pi r squared h. And so it's 1/3 pi r squared is 4 times its height, which is also 4, which is 64 pi thirds. So I know I did it correctly, but I did it a way cooler way. I know, a way longer way, harder way, but a way that is now, we're about to get to a problem that you can't use a shortcut for, and there's not going to be a way to check it. Consider the shape that is generated if y is equal to x squared on the interval from 0 to 3. So when you go to make your graph, you have to plan ahead a little bit. It's really easy to make the mistake of thinking, oh, it's an upward parabola, I just need that first quadrant. But remember, we're going to rotate it around the axis, so you need to make sure you leave room underneath as well. I do need to get up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I do need to get out to 3, which I'm going to exaggerate my points just to make it easier to see. So 0, 0, 1, 1, 2, 4, and 3, 9. There's my parabola. I'm going to rotate this around the x-axis. So now I'm going to have points at 1, negative 1, 2, negative 4, and 3, negative 9. So my question to you is, and I'm going to stop at 3, what shape does that make? So again, if you can't picture it, you can cut out just this shape right here for yourself. So cut out a little parabolic shape there that's been cut off and stick it on your pencil and rotate it around, and then you'll be able to see it. So I like to think of this as you have a sheet and then you pull it up in the middle. If you pull it up in the middle, it's going to do this. It's not strong enough. It's not firm. So it's not going to make a cone. It's going to make this, if you just like take a sheet and you pull it up in the middle, it's going to have that arched look. Or you might think of it as a circus tent top. So that's the shape that it's going to make. I apologize. I am not that great at drawing these shapes, but hopefully you're imagining it in your head. But what's cool is that if you were to run my tent top through a slicer, we'll put the slicer over here this time. So I start making slices, I'm still going to get these discs, these circles. Calculus, we call them discs. So I'm going to add up a bunch of circles. If you always start with pi r squared in the integral, that means you're adding up a bunch of circles. I'm going to start my slicer at 0, and I'm going to keep slicing until I get to 3. And the radius is going to keep changing. So my radius of each one of these circles is going to keep changing, and it's going to change based on where the x value is following the x squared formula. So I can actually say that x squared is my formula. So if you're not the kind of person that's willing to listen to me, which is a lot of people get this one wrong because they think that they can remember the square. They don't want to do this step first. And so they just write, oh, it's going to be pi r squared. And then they put in the x squared, and their mind sees the square and thinks they've already done it. But it's actually x squared squared. This one is for the r squared, and this one is your r. So be careful. I would just draw the parentheses and the square first. And as an AP grader, I see this all the time. So be careful. Okay, so pi integral from 0 to 3 of x to the 4th. These are nice, easy problems to do. Gives us pi x to the 5th, meaning, not that these are easy problems, meaning that the integral itself is a fairly straightforward integral. 3 to the 5th is 243. And when I plug in a 0, I do get 0. So this is my final answer. So let's go ahead and show you the formula that you would see in a book, which is the volume of a solid of a known integrable, which means you're able to take the integral, of a known integrable cross-section area A of x from A to B is the integral of A from A to B. Volume is equal to A to B, A of X. They make it sound so complicated. So the reason they just leave this as area, so your area of that cross section is, we are eventually going to do different cross sections. We're going to make squares and triangles and other things, but today we're just focusing on discs. So for now, this area is always going to be pi r squared. So if you would like to try this next one on your own, I'll tell you that the answer is 2 pi, but of course I am going to do it for you. The volume of a solid formed by the region bounded by the graph of f of x is equal to the square root of sine of x. So you may be thinking, why did they do that? I don't know what the square root of sine of x looks like. You do. We'll figure it out. So here's pi halves, here's pi. So let's think about what we do know about sine. Sine of 0 is 0. The square root is still 0. And we know that sine of pi is 0, so the square root of 0 is 0. And pi halves, sine of pi halves is 1, and the square root of 1 is 1. So some of our points didn't even change. So normally sine would look like this. How is this going to look different from it? Well, let's take the point, let's say there's some point at which it's 0.9. It's going to be the square root of 0.9. So what would be the square root of 0.9? I don't know. So let's make an easier one. At some point, sine is going to be 0.81. So when sine is 0.81, what's the square root of 0.81? 0.9. So it's going to be a little taller. So that's how you can think of this graph. This graph is just going to be a little bit taller. It's going to get there faster and then go down like this. Is that going to affect very much? No, because when you flip this over the x-axis, so you just want to try and reproduce it as best you can. And I run it through my slicer, it's still going to make a bunch of discs. Even if they had just chosen sine of x, it was still just going to make a bunch of discs. So what do I want to do? I want to add up, which is to integrate all the area of all these discs. I'm going to go from 0. I'm going to stop my slicer at pi. And what is my r squared? So always do this. Oops. Always do this, r squared. And what is this radius? What is the distance from here to here each time? How is that? It keeps changing, right? And how is it calculated? It's calculated by plugging it into this formula. Now do you see why they made you do square root? Harder to graph, little harder to graph, but it will make your integrals so much easier because now this is just going to be, I took the pi out, 0 to pi of just sine of x. So I know it looked like they were being mean at first, specifically me being mean, right? But in the end, it's actually kind of nice. Okay, so the integral of sine of x is cosine of x, but since the derivative of cosine is negative sine, it must be negative. I'm going to put this negative way out in front with the pi so it doesn't look like subtraction. If you put it here, somebody might think it's subtraction. So I'm going to put it out in front with the pi. Negative pi from 0 to pi is negative pi times cosine of pi minus cosine of 0. This is one where cosine of, when you plug in a 0, it does give you an answer. Cosine of pi is negative 1, and cosine of 0 is 1. So negative 1 minus 1 is negative 2, but then there's a negative there, so positive 2 pi. And that's my answer. All right, hopefully you're getting the hang of these. Find the volume of the solid formed by revolving the region bounded by f of x is equal to 2 minus x squared and the x-axis about the x-axis. So let's go ahead and draw this. So the y is a downward parabola that has been moved up 2. Its x-intercepts, when this is equal to 0, is going to be plus or minus the square root of 2, which is approximately 1.4. So somewhere around there. So it's going to look like this. I really don't need the entire thing. I'm just looking at this section right here. And that's what I'm going to rotate around the x-axis. So it's easy just to kind of mimic the points and then try and flip the shape like a mirror. So this is going around the x-axis, around the x-axis. Again, you could put this blue shape on your pencil with a sticky note and wrap it around, and you would see this shape. So my volume, I'm going to start my slicer at negative square root of 2, and I'm going to keep slicing until I get to positive square root of 2. And I'm going to do pi r squared. What is my radius each time? My radius is just this function value, 2 minus x squared. So I get, take the pi out, negative square root of 2 to the square root of 2. When I expand this, I get positive x to the 4th minus 4x squared plus 4, which is x to the 5th over 5 minus 4x cubed over 3 plus 4x from negative root 2 to positive root 2. This looks perfectly terrible, doesn't it? It is a little bit awful. So pi times, okay, so I really want you to think about this. The square root of 2 to the 5th is the square root of 2 times 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 the square root of 2. So this is 2, and then this is 2. So 2 times 2 is 4 square roots of 2 over 5. And you can do the same thing with this one. The square root of 2 of the square roots of 2 make 2. So minus 8 square roots of 2 over 3 plus 4 square roots of 2. I went through all that trouble because I wanted them all to be just in square root of 2. Minus, now I have to do the same thing with negative square root of 2. So fortunately, it will produce the exact same numbers, but they'll be opposite. So this is still going to be 4 square roots of 2, but because it's an odd power, it is going to be negative 4 square roots of 2 over 5. And then this one's going to end up being positive 8 square roots of 2 over 3. And this one will end up being minus 4 square roots of 2. And if you're thinking, would they ever give me one this hard on the AP exam? Well, they might. Fortunately, if they do, you can stop here. You don't have to finish as soon as you've plugged it in. You're good to go. But if it's a multiple choice one, then you'll have to finish it. And they do usually put on one question where they want to see if you can do some basic math. So the common denominator, well, first of all, this will give you the 4 and the 4 make 8 square roots of 2 over 5 if I distribute that negative. And then this one, they're both going to be negative, minus 16 square roots of 2 over 3, and then plus 8 square roots of 2. So I do want to get a common denominator, which is going to be 15. So this is 24 square roots of 2. And this is going to be 16 times 5, which is 80 square roots of 2. And then 8 times 15 is a whole number, so plus 120 square roots of 2. So that gives you 24 minus 80 plus 120 is 64 square roots of 2 over 15 pi. That was really hard. If you did it on your calculator, you would get 18.956. But if you're allowed to use a calculator, then I would like to think you would use a calculator way back up here at this step. Okay, so on your calculator, it would come out to be 18.956. So how could I have made this just, literally tiny bit easier? Another option would have been to change this to a 0 and then put a 2 out front. Because it has symmetry, you could just go from 0, find the volume from 0 to the square root of 2, and it would be the same as the other volume. And that would have saved you this step right here, which might have made your life a little bit easier. But regardless, definitely a hard problem, so great job. Number 3, find the volume of the solid formed by revolving the region bounded by y is equal to the square root of 16 minus x squared, the x-axis and the y-axis. Ooh, about the y-axis this time. So first of all, do you recognize this formula yet? I'm hoping that you do. Let's show it to you in a different way and see if you recognize it. I'm going to square both sides. I'm going to add the x squared to the other side. Do you see it yet? It's a circle, but it's only a half a circle, because if I were going forward with this, if I had started with a circle and then tried to get y squared or y all by itself, I would have plus or minus the square root of 16 minus x squared, plus being the top half of the circle and the minus being the bottom half of the circle. So this is just the top half of a circle. So let's go ahead and graph that. 1, 2, 3, 4. It does have a radius of 4. Zero, zero, or not 0, 0. Negative 4, 0. So let's see if we can draw this well. It's not great, but it'll have to do. So what's interesting about this one is that it's bounded by the x-axis, the y-axis, and it's going around the y-axis. So when you first read it, you might think, well, this side would be bounded by the circle and the x-axis and the y-axis, but so would the other side. You know what? That's okay, because it doesn't actually matter which side you do. When you go around the y-axis, you're still going to get the exact same shape, which is going to make a dome of some kind. So here's your first circle. So we're doing them horizontally this time because we're going around the y-axis. And we're still building circles, but I like these better because you can kind of picture it. If you were, if you had circles sliced together and you kept adding them up, you could make this dome shape as long as you made each circle incrementally smaller. So my process is still exactly the same. I'm going to do the volume. I'm going to start my slicer at 0. I'm going to keep slicing until I get to 4. And I'm going to add up a bunch of circles, pi r squared. So what's my radius this time? So my radius this time does change because I'm going around the y-axis. It's this distance right here, which is x. So I need to make this equation x is equal to. Well, that's okay. I can do that. So right now it's x squared plus y squared is equal to 16, just to move it back. And I want to get the x alone. So x squared is equal to 16 minus y squared. X is equal to the square root of 16 minus y squared. So it just changed it. It actually ends up looking identical, 16 minus y squared. But because we're going around the y-axis, we do need to do dy. Everything's in terms of y. Now, if you were to do this one on your calculator, ironically, you would change it back to x's because we always use x's on our calculator. But we'll do it by hand. The volume is equal to, I'm going to put the pi on the outside, from 0 to 4. Fortunately, this is just because the square root is being squared, it's just 16 minus y squared. So 16 minus y squared dy is going to be equal to pi times 16y minus y cubed over 3 from 0 to 4 is equal to pi times 64 minus 64 thirds minus, and unfortunately when I plug a 0 in, I do get 0 for both of them. So to change this, you do need a common denominator. So 64 as an over 1 becomes 192 over 3 minus 64 over 3 pi, which is 128 thirds pi, which reduces to 42. I guess it doesn't reduce, but 42 and 2/3 pi. All right, number 4. Find the volume of the solid formed by revolving the region bounded by y is equal to x to the 2/3 and x is equal to 0 and y is equal to 1. Again, we're going to go about the y-axis. So we just got a little experience doing that. So I'm going to bound this by y is equal to 1, so I'm not going to go very far, and x is equal to 0. And this function, which if you're not familiar with what it looks like, you can always make a graph. Plotting points is your go-to. So 1 to the any power is still 1. You might want to think of this as the cube root of x and then squared. It'll help you think of your next number. What number do you know the cube root of? 8. The cube root of 8 is 2, and 2 squared is 4. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. So this is what it looks like on this side. And because it's being squared, it is even. So even if you put in a -8, -8 cubed is -2, but then squared goes back to +4. And the same thing with the 1. So it looks something like that. However, we actually are only looking at it up until y is equal to 1. So this line right here. So we're bounding the region by this curve and by x is equal to 0 and y is equal to 1. So like last time, I only want one of these two sections, but it doesn't matter which one you pick, because as soon as you start to revolve it around, they're going to look the same. So this is very similar. By the way, this is called a cusp. Very similar to my tent, my circus tent problem. It has this shape to it, but of course it's upside down. So fortunately, the basic premise doesn't change. The volume is still going to be pi r squared. But because I'm going around the y-axis, everything must be in terms of y. This is dy. This is y. I'm going from 0, and I'm going to make these until I reach a height of 1. It happens to be also 1 in the x direction, but that's not where I got that from. That is the y. And then now I need to know what this distance is in terms of y. So this distance is x, and x is equal to, well, if y is equal to x to the 2/3, how do I get what x is equal to? I can raise both sides to the 3/2. So x is equal to y to the 3/2. Y to the 3/2. So if you're going around the y-axis, your equation better be rewritten so that y is in it instead of x. And I can simplify this. You can take out the pi if you want to y cubed. How lovely. So the volume is just going to be pi y to the 4th over 4 from 0 to 1. When I plug in a 1, I get pi fourths. When I plug in a 0, I get 0. And so my answer is pi fourths. All right, let's do another one. 2 more. Find the volume of the solid formed by revolving the region bounded by, oh, we've done this one before, right? 2 minus x squared, and g of x is equal to 1. About the line y is equal to 1. So we're not going about the x or y axis this time. So as usual, they get more complicated. So we know from last time, graphing this, that this has a height of 2. It's a downward parabola, and it crosses at 1.4, which is the square root of 2. So it looks like that. But I also want to graph the line g of x is equal to 1, which is this line right here. And I want to rotate around that line. So this is my region. Oops, that is definitely not what I wanted to do. Sorry. So this is my region right here. Okay, so that's what I'm gonna rotate. So it goes one above that, so it goes one below that, and you just want to try and mimic it, mirror it. And if you go around that line, it's going to be like going around an x-axis. So it's going to look like this. Always start the same way. The volume is adding up a bunch of disks that all have the area pi r squared. Okay, this is the most important one we're doing today. So the question is, what is the radius? What is this distance right here? Every time. How can you find it? It's not all the way anymore. It's not 2 minus x squared. You can't just always use the function. But in this case, 2 minus x squared would give me this. But since I just want a little piece of it, I'm going to have to keep subtracting 1 each time. So my formula is going to be, for my radius, is going to be 2 minus x squared. That would give me the full height minus 1. And where am I going to start my slicer? I'm going to start my slicer. Oh, I have to figure out where that intersects, right? So I'm not going all the way to negative square root of 2 like I did in a previous problem. I need to know where this intersects. So 2 minus x squared is equal to 1. And that's nice and easy. 2x squared is equal to negative, or minus x squared is equal to negative 1. X squared is equal to 1. X is equal to plus or minus 1. So it's going from, which is what it, okay, it looks like on this side. On this side, it doesn't look perfect. From negative 1 to 1. Or this time, let's start at 0. When the two sides are symmetric, we can do that, which is kind of nice. Okay, so let's go ahead and simplify this. Dx. I always forget that. 2 pi, and this is actually going to be 2 minus 1 is just going to be 1 minus x squared. So that's going to give me x to the 4th minus 2x squared plus 1 dx from 0 to 1. The volume is going to be x to the 5th over 5 minus 2x cubed over 3 plus x from 0 to 1. When I plug in a 1, I get 1/5 minus 2/3 plus 1 minus, when I plug in a 0, I get 0. But notice I keep doing it. I keep plugging in 0 because sometimes you do get a number there. And we're almost done. We just need to give this a common denominator. This is 3/15 minus times 5, 10/15 plus 15/15 is 18 minus 10 is 8/15 times 2 is 16/15. So this last one is very straightforward. It doesn't teach you anything new. So if I were you, I would try it on your own and see if you can do it. The answer is 8 pi. But of course, I am going to do it for you. Find the volume generated by revolving the region bounded by the curve y is equal to the square root of x, and the lines y is equal to 0 and x is equal to 4 about the x-axis. So y is equal to the square root of x, 0, 0, 1, 1, 4, 2. Remember back in algebra 2 when that was the big thing? You just had to graph that. Now it's just the first step. The line y is equal to 0, which is the x-axis, and x is equal to 4. So I'm going to go around the x-axis, which means I'm just going to mirror it. And it's going to make a bunch of disks. So I'm going to make my integral. Volume is equal to the integral, which means the sum of all the disks. The disks are all pi r squared. My radius each time is the square root of x. See how nice they were to you? Because that's just going to end up being pi x. Nice, easy integral. Don't forget your dx. In my limits of integration, I'm going to start my slicer at 0, and I'm going to keep slicing until I get to 4. So from 0 to 4 of pi x dx is equal to pi x squared over 2 from 0 to 4. 4 squared is 16 over 2 is going to be 8 pi. All right, that's it. That's the last one. Have a great day.